Afternoon. We are continuing from our class in the morning, where we actually talked about pressure drop through a circular tubes and derived the expression for Hagen-Poiseuille equations. And then we talked about the drag force, the role of friction factors. So in the first half, the talk was mainly confined with fluid flow when the fluid behavior was laminar in nature. Okay, we did not consider the fluid flow behavior when the fluid becomes turbulent. So this time we're going to talk mainly about the head loss or the pressure drop which happens when the fluid is turbulent in nature. Okay, so the second half is actually going to be mainly discussed with the fluid behavior which are turbulent in nature. So let us first examine what is turbulent flow in pipes, or how does it develop. Okay, so if you remember, I think in the initial classes I talked about that most of the engineering applications, okay, it deals with turbulent flow because it's very difficult to maintain laminar flow unless the fluid is very highly viscous in nature and flowing through a short tubes with the small diameters. But since turbulent flow is complex mechanism and it has a lot of eddy currents being involved due to a lot of fluctuation in the velocity profile, so the derivation of expression of that in dealing with turbulent flow, it requires a huge amount of like works. Okay, and there is a lot of complex equations also being involved. Okay, so what happens? People actually use a lot of iterations method to derive pressure drop or head loss or the volumetric flow rate, and a lot of for doing so, a lot of experimental work, a lot of like trial and error methods are also being implemented. Hmm. Now, before going into details, the first need to know like what is turbulent flow. Actually, turbulent flow is characterized by rapid fluctuation or some sort of like vortex formation, swirling action in the fluid behavior. So this is actually known as eddies or eddy currents. Okay, and this happens throughout the path of the fluid flow. And there is also a lot of additional momentum and energy transfer also being involved. In laminar flow, I think I talked about the fluid particle flow in an ordered manner. Okay, and it's ordered manner, it's a streamlined flow. There is no deviation in the fluid path. Hmm. And momentum and energy are transferred across the streamline by molecular diffusion. Whereas in turbulent flow, due to the eddy formation, there is a momentum and energy transfer to other region of the flow occurs, and the molecular diffusion is negligible. Okay, and as a result, turbulent flow is associated with much higher value of friction. So that is the one aspect. When you talk about turbulent flow, there is high value of frictions happen, and then due to this frictional loss, there is a lot of pressure drop and head loss occurs in the turbulent flow. The eddy current or the eddy motion in turbulent flow causes significant fluctuation in the velocity profile, temperature, pressure, and even the densities if it is a compressible flow. Okay. So let's look at the velocity profile of a turbulent flow. If you monitor closely, as you can see, we have a mean velocity, right? That is given by u bar. Okay, that the mean velocity. But then, respect to the mean velocity, the velocity is not constant. It's fluctuating. It's going plus and minus. Okay. So if you have to derive or draw an expression for velocity profile, which is given by u, so that will be always like the mean value of the velocity plus the fluctuating component, which is given by u prime. You can see this is the u prime. That is that the velocity profile will be u bar plus u prime. Okay, that is how you derive the turbulent flow. Now, turbulent flow always associated with some sort of shear stress. Okay, I mean obviously when you talk about laminar flow, we have already seen that the laminar flow also associated with the shear stress. Due to the shear stress at the wall, there is a pressure drop, right? And this pressure force and the shear force actually balance each other. So the same phenomena occurs when the flow is turbulence in nature. Now, during turbulent shear stress, this actually there are two parts, which is one is the laminar parts, which accounts for the friction between the two layers of the fluids in the flow direction, right? Which is given by tau lam is minus mu du bar by dr. So this is just like what actually happens during laminar. Another is the turbulent component, which account for the friction between the fluctuating fluid particle and the third bond, and this is given by tau. Okay, so this is actually due to the fluid particles are fluctuate in respect to a mean velocity. So due to that, there is a turbulence component. Okay, so the total shear stress due to turbulence can be given by tau total equal to tau laminar plus tau turbulent. Okay, so what happens the turbulent shear stress if you actually expands the terminology? So the total total shear stress given by tau total is equal to mu plus mu t del u by del y, which is mu is actually the mu actually for the laminar flow and mu t is for the turbulent flow. Okay, mu is the viscosity. Okay, this is actually known as mu t is known as eddy viscosity or turbulent viscosity. So that mu actually, if you know that kinematic viscosity also given by nu, right? That is mu by rho. So if you just turbulent viscosity can also be replaced by nu t, that is kinematic eddy viscosity or kinematic turbulent velocity. So this expression will become like this. Okay, rho into nu plus nu t into del u by del y. Okay, so this is actually the total shear stress due to turbulence. Now, the most important thing, if you closely monitor the velocity profile or the velocity behavior between a laminar flow and the turbulent flow, you must observe that the turbulent flow, the velocity gradient is very steep, okay, compared to the laminar flow. As you can see, this is a laminar flow. It's not so steep, but in case of laminar flow, the velocity profile is very steep in nature, okay, because there is always fluctuation in the y directions. And obviously, for doing that, the shear stress, the wall shear stress, is very high or very large for turbulent flow compared to the laminar flow. Now, let us look into the velocity profile. I think this schematic diagram you must have seen in the first half. This is for the fully developed flow, which is laminar in nature, and this is the average velocity, which is generally half of the maximum velocity, that is v at this point, v max at this position. Okay, and the wall velocity is 0 due to the shear stress. Okay, and this is radial direction. UR is given the velocity profile. So this is actually already you encountered in the first term, and this happens when there is a flow is laminar in nature. Now, what happens when the flow is turbulence in nature? Okay, so you can see here, this is pretty much full in nature. Okay, the turbulence flow is very polar in nature, and it has many layers, starting from viscous layer, buffer layer, overlap layer, and turbulent layer. Okay, and it actually consists these 4 regions. And I think I have already discussed all this different fluid region when we talked about boundary layer concept. So actually, again, to rehearse our memory, the very first thin layer is actually the viscous sublayer. Okay, where actually the viscous effect is dominant. And if you remember, like Osborne Reynolds, which when he derived the expression for Reynolds number, he talked about the Reynolds number is nothing but the inertial force was the viscous force. So obviously, if viscous force is the dominant force in this particular case, it will be streamlined or laminar in nature. The velocity profile in this layer is very nearly linear and flow is streamlined. Next to the viscous sublayer is buffer layer. I think you have already seen this is the buffer layer, sublayer, above the viscous sublayer. So here actually the turbulent effect are becoming significant compared to the viscous sublayer. But the flow still remains viscous streamlined nature. Next to that viscous buffer layer is the inertial sublayer, where actually turbulent effect are much more significant. And finally, the outer layer, which is turbulent layer, where turbulent effect become dominant due to the molecular diffusion effect. So the flow characteristics are quite different in different region, and this is it is difficult to come up with an analytical relations for velocity profile. So unlike laminar flow, which are very straightforward, you have considered a particular, velocity profile like given by UR, which is actually varying in the radial direction. This is not so straightforward when it comes to turbulence flow. So that's why it is very difficult, and we will see in the later half that there is a chart for that. You need to determine various parameters to know, like head loss, pressure drop, and other parameters. Okay, so let us move forwards and then and see what is happens, how is the velocity profile derived, how is the velocity profile expression comes into picture when it is turbulent flow. People have seen that it's mainly a power law velocity profile is better fit for turbulence flow. That's why it's known for turbulent flow. It's a power law profile, and it's given by U by U max is equal to Y by R to the power 1 by N, or it can be given by U by U max 1 minus R by R 1 to the power N, because Y is nothing but, if you remember first of also we talked about this, that is capital R minus small r, that is the radius minus the distance traversed in the radial direction. So that this is expression, perfect expression, Y U by U max equal to 1 minus R by R to the power 1 by N. Now what is N here? The exponent N is a constant, and whose value depends on the Reynolds number. Okay, the value of N increases with increasing Reynolds number. Generally, N starts with 7. That is the approximate value for turbulence flow. And 1/7 power law, it's sometimes known as 1/7 power law velocity profile for turbulent flow. So as the Reynolds number increases, n increases, and as you can see, for laminar flow, it is pretty flat, right? And what happens when n increases, it's become power law functions comes into picture, and then you can see n6, n8, and n10. The power law profile cannot be used to calculate the wall shear stress. Okay, it's very difficult to calculate wall shear stress. It gives a velocity gradient of infinity there. Okay, as you can see, velocity gradient is pretty infinite over here, and it fails to give zero slope at the center line. So that's why we need to do some trial and error method and to determine various parameters. And it's and one thing is that turbulent flow velocity profile is very fuller than the laminar one. Okay. So what happens? How did the people find out various parameters? So one more aspect when it is turbulent flow is that there's always some sort of surface roughness associated with it. The friction due to the we generally consider it's a smooth wall, but actually in reality, the pipe or the tube or any duct through which the fluid is flowing is not so smooth. There is some sort of surface roughness always there. The surface roughness is given by the epsilon, okay, and the relative roughness is given by the epsilon by d, where d is the diameter of the pipe. So Colebrook was scientist. Actually, he derived this expression for turbulent flow, that 1 by square root of f minus 2 log epsilon by d divided by 3.7 plus 2.51 divided by Reynolds number square root of f, where f is the friction factor, also known as Darcy friction factor. And this expression cannot be solved. So what people have found, they have derived various parameters, relationship between Reynolds number and friction factor for various epsilon by d, which was plotted in a chart that is known as Moody's chart. I'll show that in the next slide. So Moody's chart actually helps to determine, it's a very well-known chart, Moody's chart, and it has been used to calculate either Reynolds number or friction factor, which are very critical parameters, but various epsilon by d parameter, because epsilon b is not it's constant, it's a variable. Okay, so as the epsilon and d varies, you can get a relationship between f and Reynolds number, and then using that Moody's chart, you can calculate the parameters. It's most widely accepted and used chart in engineering fluid dynamics. Although it is developed for circular pipe, but it can be used for non-circular geometry by replacing the diameter by hydraulic diameter. And I think hydraulic diameter is what I have already discussed in the last class. So you can see here, this is a Moody's chart. What is actually happening here? The y-axis, you can see Darcy friction factor given by f, and the x-axis is given by Reynolds number. And as you can see, these lines, all these lines actually corresponds to various epsilon by d parameter. Like it is given epsilon by d 0. So as you move here, the various epsilon by d it comes into picture. Here you can see like 0, 0 0.05, 1, 2. So it's given, all the lines are given, okay, 0.002. So various epsilon by d parameters, relative roughness, that is known as relative roughness. And as you can see, this is the laminar region, f is 64 by RE, that is the relationship which holds. Transition region, this is the region, and then turbulent flow. The moment it crosses this has become turbulent flow. Using this chart, if you know your relative roughness, you can easily calculate what will be the value of either Reynolds number or Darcy friction factor. Most of the time Reynolds number is known, then you can calculate Darcy friction factor. Let us examine one chart. I think one table is here. So here actually what happened, roughness value is given in foot and millimeter for different material. Equivalent roughness value for new commercial pipe. So these are the commercial pipe of different materials: glass, concrete, wood, rubber, cast iron, wrought iron. Anyway, so the various parameters are given, and you can easily from the Moody's chart calculate the epsilon by d if you know the diameter of the pipe, and then you can calculate friction factor if you assume the Reynolds number is 10 to the power 6. Okay, so if you consider that 10 to the power 6 is the Reynolds number, then you can easily calculate the friction factor. So as you see, this is very straightforward. It's just to look into the chart and get the value. Now, what happens in the design and analysis of piping system, the Colebrook equation or the Moody's chart, we usually encounter three types of problem. Like, what are the three types of problem we encounter? Either we determine the pressure drop or head loss when the pipe length and diameters are given, or to determine the flow rate when the length and diameters are given for a specific pressure drop. Or we determine the pipe diameter when the length and flow rate are given for a specific pressure drop. So actually, these are all interrelated, but sometimes two parameters are given and one needs to be calculated. So the first one is very straightforward, which can be easily, solved using the Moody's chart or by using the parameters for Moody's chart. But the second type and third type are commonly encountered in engineering design with the selection of pipe diameter, for example. The use of Moody's chart is required an iterative approach because the parameter is not can be easily directly found from the Moody's chart. So that what happens to avoid this tedious iteration method, Swami and Jain came up with some equation, some explicit relationship in 1976, which actually matches within plus minus 2% from the Moody's chart value, and the expressions are like this. So we have already seen in the Colebrook equation we can deep the pressure drop. Now they come up with this novel equation. Then you can, beside the pressure drop, which can be easily calculated from the Colebrook equation, they have calculated the volumetric flow rate and diameter of the pipe. And this is the relationship. This is very handy. You keep this relationship with you whenever you need to solve a numerical. This will be very useful. I think you all know the parameters here. It is the volumetric flow rate. The expression due to gravity, D is the diameter of the pipe. HL is the head loss. L is the length. Epsilon is the roughness, and epsilon B is the relative roughness. Nu is the kinematic viscosity. So all the parameters are known here. Okay. So and then this relationship holds for certain value. Okay. So these are some precondition. Okay, that has to be made. Then only this relationship will vary. So anyway, this relationship will be useful as we solve some numerical. We'll see that later. I have given one numerical just like what I gave you in the class in the first talk. So please you solve this numerical. We can discuss in the next class, that is next Wednesday. All the numerical given in today's class, we can discuss next Wednesday's class. So this is my handwritten notes, and I'd like to give it to you, share it with you, and this is why it's become easy for you. So I have seen actually for the smooth pipe when the flow is turbulent. Now this relationship is for so far I have discussed about turbulent flow through rough pipe. Like what happens when turbulent flow through a smooth pipe. Okay. So then the relationship is this: F is equal to 0.079 Reynolds number to the power minus 1 by 4, or it can be 1 by square root of F 4 log Reynolds number to the power square root of F minus 0.4. So these two relationship actually you can use this one, or you can. I think this is more easy to remember. Better you use this one. F is equal to 0.079 into Reynolds number to the power minus 1 by 4. So remember, this happens only when the flow is turbulent and it's through a smooth pipe. There is no surface roughness. What happens when the flow is laminar through a smooth pipe? Then the relationship is F by 16R. I have given it to differentiate like the relationship. Okay, this is for turbulent flow through a smooth pipe. This is for the laminar flow through a smooth pipe. And these two expression, this expression is for turbulent flow through rough pipe. Remember, there is no laminar flow through a rough pipe, so the expression never holds. Laminar flow cannot exist in a rough pipe. Whenever there is a surface roughness associated with it, that has to be a turbulent flow. So this expression actually is for turbulent flow through a rough pipe. If it is rough pipe, definitely it should be turbulent flow. Now, how does this head loss or pressure drop happens in pipe fitting? I have listed out the reasons, mainly the fittings which are used in pipeline for joining two pieces of pipe or changing the direction of line, connecting branch line, controlling flow, or stopping the end of a line. Due to various reasons, there is a pressure loss, pressure drop, and head loss occur in pipe fitting. Okay, so these are the few reasons which are listed here. Let us look into the friction loss in a coils. Okay, so far we have talked about straight pipes, whether it's a smooth pipe or rough pipe. But sometimes fluid passes through some coils. Okay, so when a fluid flow through a circular tube arranged in the form of a coil, such an arrangement accommodates a long tube in a small place. Okay, like for what happens? You are gardening using a hose pipe. Okay, in the evening. So that hose pipe maybe is in a coil form. So there must be some sort of head loss, pressure drop. So that frictional factor drops in a coil. It can be given by del P coil, and which is greater than the straight pipe, which is given by del P straight. So STR stands for straight, and coil stands for COIL stands for coil. So the pressure drop in a coil can be given by del P coil is equal to del P straight times 1 plus 3.54 d by d. Now here small d is actually the diameter, internal diameter of the pipe, and the capital D is the diameter of a turn of the coil. That you remember. Capital D is not any other diameter, it's a diameter of a turn of the coil. Okay. What happens when there is a pressure drop in turbulent flow of fluid through non-circular conduit? I think we have already discussed hydrodynamic radius diameter in the first half. So let us again examine this. The frictional loss in the turbulent flow of fluid through a long straight channel of constant non-circular cross section may be estimated by the use of a equation used for circular pipes if the diameter of the in the definition of the Reynolds number and the friction factor is taken to equivalent diameter, okay, defined by the 4 times of the hydraulic radius. I think I have already talked equivalent diameter 4 times of the hydraulic radius is given by 4 into weighted cross section by weighted perimeter. So it's a annular tube, so it has a inside and outside diameter. So the outside diameter pi d square by 4 minus 4 by pi d square by I mean it's pi d square by 4 outside diameter b inside diameter a, so obviously 4 pi by 4 b square minus a square, and then weighted perimeter is pi ab pi b plus pi a. So actually whereas this time has become b minus a, or the difference of the diameter or difference of the radius of the outside and inside, the equivalent diameter from to a non-circular conduit. Now we talked about the Colebrook equation, the pressure drop expression, the Hagen-Poiseuille equations in the first half. So frictional loss, which are evident or which happens during a fluid flow through a smooth pipe or a rough pipe in engineering application in practical life. So the pressure drop, I think I have already mentioned that they are given by del Pf to F rho u square L by D. So what are the expression for force and head loss? So the expressions are, for the force it will be del Pf by rho, the density. If you divide by density, the pressure drop is from force drop, which is given by 2Fu L square by L into L by G, given the unit is joule per kg. The pressure drop was Pascal. Head loss again HF is given by rho del Pf by rho G, that is the pressure drop by rho G. It become 2F U square by G into L by D, which is given by meter. And the frictional factor is defined by F tau W divided by half of rho U square. Okay. What is tau W? Tau W is the shear stress of the pipe wall, and it depends upon the Reynolds number of the flow and the relative roughness epsilon by D at the wall. Okay. That is given in the expression. Let's move forward, and I'll show some numerical which I have derived. I think you can easily look into this. So first problem, given benzene at 20 C, given the density and viscosity is being pumped through a 50 meter of a straight pipe of 25 millimeter diameter with a velocity of 3 meter per second. The line discharged into a tank 25 meter above the pump. So calculate the pressure gauge reading at the discharge side of the pump. Neglecting inlet and outlet effect, the pressure indicated by the gauge is the head equivalent to the 25 meter vertical distance plus the required to work on the friction of the pipeline. Okay, so first you calculate Reynolds number dB rho by mu. You calculate the Reynolds number. Friction factor you can easily calculate from the relationship. I think I have already mentioned that this is a turbulent flow. Okay, so you have to use that expression. I think this expression F is equal to 0.079 into Reynolds number to the power minus 1 by 4. Because it's a smooth pipe, there is no roughness. Okay, we calculate friction factor. In the frictional head loss, just previous slide we discussed, this expression is 144.8 kilopascal. The pressure required to lift the fluid through a vertical distance 25 meter will be H rho G. H is given 25 meter, rho is given G. That is 290 kilopascal. So the total pressure head, one due to the frictional head, and then another is the pressure required to lift that fluid. The total pressure head will be these two, addition of these two, it will be together 363.8 kilopascal. Okay, that's straightforward. Let's look into another example. A kerosene storage tank drains by gravity to a tank truck. The length of the pipeline between the tank and the truck is 60 meter, and the internal diameter is 26 millimeter. That pipe which is flowing that kerosene, okay, has a viscosity of, the kerosene has a viscosity of 0.005 pascal second and a density of 800 kg meter cube. Both tank and truck are open to atmosphere, and the flow rate of kerosene is given 0.8 liter per second. Calculate the difference between the level in the tank and that in the truck. So you have to calculate the head, okay, head loss. So first you calculate the turbulent flow. It's a smooth pipe, but it's a turbulent flow already given because it's a turbulent flow. So you use this expression. You can actually check it, Reynolds number also. very high. So you calculate from that turbulent, and velocity of the kerosene can also be given, because volumetric flow is given 0.8 liter per second divided by area. So it will become 1.51 meters per second. Reynolds number is this much, so F will be 0.005 from this expression. Now frictional pressure drop will be HF 2F U square by G L by D. So you put all the value and you get 5.37 meter. Okay. All the pressure in the 1 atmospheric pressure, horizontal velocity is 0. So therefore, using Barnow's equation, the head loss will be 5.37 meter. Let us move another example. Determine the loss of pressure in overcoming the friction in a coil through which water flows with a velocity of 1.2 meter per second. The coil is made of a well used steel pipe with an inside diameter of 330 millimeter. Epsilon given 0.2 millimeter. So there is a surface roughness is there. Okay. The diameter of the turn of a coil is given 1 meter. The number of turn is 10. The average temperature of water in the coil is 30 C. For water, 30 C, density and viscosity are given. So first is the Reynolds number. You calculate all the using the parameter is 4.49 into 10 to the power 4. Epsilon by D is given 0.067. So using that expression, this is a turbulent flow. And first of all, this is turbulent flow, and then it's a you need to know the friction factor. So using this expression, you can calculate friction factor 0.0088. The length of the steel pipe forming the coil is IDN, right? So diameter of a turn given, number of turn then given. So diameter to the L is 31.9 meter. For a straight pipe, I mean, if you consider it's a straight pipe, what is the pressure drop? This expression 2F U rho U square L by D, that is 26.5 kilopascal. Now, if it is a coil, since forming coil, so what will be the pressure drop? That expression you use, and then it will be 29.6 kilopascal. So you see that for a straight pipe and a coil pipe, with the pipe is in a straight position or in the coil position has a higher pressure drop. Okay, because of that formation of the coil. That is you have to remember. Next one is water at 21 C, given density and viscosity, is flowing at a velocity of 3 meters per second. In the annulus between a tube with an outlet diameter 25 millimeter and another with an internal dia of 50 millimeter. In a concentric tube heat exchanger, calculate the pressure drop per unit length in the annulus. For steel, take epsilon 40 into 10 to the power minus 6. So that equivalent diameter, I think I have already shown that it will be B minus A. It will be 25 millimeter. Reynolds number, it is 75,000. Epsilon by D, equivalent is given 0.0016. So you calculate F 0.0062. And then you can calculate, actually this F can also determine from the Moody's chart. I have calculated, you can cross verify it is in Moody's chart. Okay, all these things. Now pressure drop will be here del PF by L. So this expression will be 4.464 kilopascal per meter. Because it has to calculate pressure drop per unit length. Okay, you have to divide by L.